All right, good afternoon and welcome to BayOne Bootcamp. Today is Tuesday, September 1st, and let me know, folks, when you can see my screen. Can you see my screen? Yeah.
Yes.
You're able to see your screen.
Okay, wonderful, wonderful. And please mute yourselves, folks. Yeah, thank you. All right, so welcome to our Tech Bootcamp. We've started this in June of this year, so we've already completed 3 months. And thank you for those of you who have been attending all of our sessions right since the beginning. Thank you very much. All right, so this is us. We are committed to your success. These are challenging times, we understand. And these technical boot camps are a way for us at BayOne to give back to the community. We work very closely with women in technology. Many of you on this call have joined us through one of our Women in Technology forums. We also work with several diversity and inclusion and equity initiatives. And we are proud to be able to work in that regard. And those of you who are joining from one of those forums, very welcome to these tech boot camps. We truly appreciate your participation, and please continue to join us in the future as well. All right, so what are these tech boot camps? We meet once a week, every Tuesday, and we cover several topics on software development, particularly digital technologies like big data, IoT, cloud computing, DevOps, AI, and ML. And in that regard, of course, the last few months, the focus has been primarily on software development related content, both front end and back end. We have had technologists join us as guest speakers like we have today from companies like LinkedIn, Facebook, GE Digital, and Apple and various other companies. So we greatly thank them for their participation and contribution back to society as well. And at the same time, also from folks like you, those who have joined us, because these are very open-ended sessions. So we have participants as young as high school grads to very senior people as well. So everybody is welcome to join, whether you are preparing for your next technical interview or whether you just want to dabble in technology. The content of most of our topics is somewhere in the middle. It tries to balance between technical and interesting content. But sometimes, depending on the topic, we do get into the technical realms as well, like we did last week when we talked about chatbots. There was a discussion around AI, machine learning, and natural language processing. All right, so this is me. My name is Suva. I'm with BayOne. We meet every Tuesday, like I said, 90 minutes, 4 to 5:30. And usually the sessions are so interesting, the Q&A session goes way beyond 5:30, but we try to end by 6 p.m. at the very latest. So those of you who are joining us for the first time and would like to continue on in our future sessions, do remember to mark your calendars for a couple of hours, okay? The Zoom link is sent typically a day in advance, else the same day as the meeting. And the reason we do that and we keep changing the Zoom link is to minimize any Zoom bombing or any kind of, inappropriate behavior. And at the same time, we expect that everybody on the call is registered by sending an email to bootcamp@bayone.com, as most of you would have probably done, right? So welcome to these sessions. Also, for a limited time, we are offering free mock interviews. If you wish to be technically screened through one of our internal experts, you're more than welcome to reach out. Now, we do have a fixed bandwidth. So this is first come, first serve. Send us your resume, including what area you would want to be interviewed on. Send the email with the attachment to bootcamp@BayOne. If there is availability, we'll get back to you. And when you come for those sessions, please prepare. Okay, prepare as much as you can, because here are the stats from recent screenings. Typically, we find that barely 2% of candidates are adequately prepared for interviews. And it's sad but that number keeps decreasing. Last summer, that number was around 6%, and steadily it has continued to decrease. And with the situation of COVID, there are more consultants on the market right now between jobs looking for a new project. If this is the level of preparation that you bring to the table, it is going to be very hard to be successful in an interview. Okay, so folks, please continue to prepare. preparing for interviews when you're transitioning between jobs is also a full-time job. So please give it, due diligence and put in as much effort as possible. We wish you all the best. Now, last week we had a guest speaker, Rishi Agarwal, CEO of Tech Vision. He talked about, particularly about natural language processing and the evolution of chatbots. We sent him a thank you note on LinkedIn, and those of you who have seen that and thanked him, thank you very much. Those of you that haven't yet, please go ahead and put in a small word of thanks, because they're all volunteering their times, all of our speakers, and we want them to come back here and talk to us again about cool things, right? So please remember to thank them. All right. Likewise, today we have a return guest speaker, Sandeep Ayloo. He was formerly at GE Digital. Now he's a senior software developer at Thales Security. And last time, for those of you who attended his session a couple of months ago, he talked about database sharding and consistent hashing. He talked about that ring, if you remember, very interesting example. And there's a lot of interest on consistent hashing, particularly among the FAANG companies these days. And there are a lot of interview questions also being asked in that regard. So I presume those of you who attended that session found it very helpful. So Sandeep has returned back to us again. He's going to talk to us about recursion in particular. He's going to tell us why recursion is different and why typically as human beings, we're so used to thinking linearly, right? So whenever we design any solution, whenever we write our own algorithm, the first thing that comes to mind is some kind of an iterative approach, right? The first hunch is to write a for loop. The challenge with the for loop is immediately, if you need to scan the data more than once, there is another for loop embedded in between. And then gradually the complexity starts increasing exponentially, right? Or at least quadratically, n squared, and sometimes worst case scenario, maybe even n cubes and more. Recursion is definitely a better way to go. It's not very intuitive. So you have to sort of program your brain. Given a problem, how would you want to convert that into more of a recursion problem and try to solve it that way, right? At least from a code perspective, it's very efficient code. Of course, you use a lot of stack, so there is usage of space as well. But then I would let the expert talk about these things, the world of recursion, how it is different, some examples. Maybe he'll take up a couple of Leetcode problems as well, talk to you about time and space complexity. And depending on time, we may touch upon dynamic programming to some extent today. Otherwise, we'll do it in a future session. So with that being said, I'll just pause here if there are any questions regarding the content that I've covered so far. Okay, if not, Sandeep, Ayloo, welcome to BayOne Tech Forum once again.
Thanks, Suva. Thanks. Can you make me as a host so that I can start presenting?
Absolutely, Sandeep. I'm going to make you a co-host right now. Okay, Sandeep, go ahead. You are the co-host.
Okay, sure. Let me just, yeah. Are you guys able to see my slides?
Yes, we can.
Okay, let me start presentation. Okay, so today's topic is basically recursive programming. Before I move to recursive programming, I just want to give some idea about how do we do programming using iterators. Then we'll talk about a different programming paradigm called recursion. Then what are the nitty-gritty details of recursion, like what happens when you do actual recursion. And then we will do a sample problem using recursion. And then for any piece of code that you write, it obviously takes some space and takes some time. So let's see how much time or space does a typical recursive code takes. And then we will do a brief introduction to dynamic programming. So I'm planning to have this session in such a way that if it takes more time in discussion, then I will do a logical stop. And then maybe the rest of the topics we can take it some other time. But I have like 30 slides here today. So there's a lot of content. So let's go about talking about this whole recursive programming paradigm. Why recursion? Why did even computer scientists thought about recursion and all that stuff? So myself, my name is Sandeep Ayloo. I've already done one session with BayOne on consistent hashing, and this is my second session, that is recursive programming. So let's start with, first, even before we go to recursive programming, let's go with programming using iterators or iteration, okay? So as human beings are basically logical in nature, and we always tend to do things in routine, like we always have a set routine. And one of that, to capture that aspect of human behavior in programming, we have something called iterators, and that is a programming paradigm where we execute a piece of code till a certain condition is met. That's the whole idea of iteration. And there are many high-level constructs that we have in different programming language like Java, C++, Python to execute a piece of code iteratively. One such programming construct that we have in Java, let's take Java as a reference language here, is for loop. Let's see the syntax of the for loop here. The for loop is pretty straightforward. It's just an initialization. You have a condition check, and you either increment it or decrement your condition variable so that you can execute that piece of code. And this is pretty straightforward, no-brainer. There's nothing complexity involved here. You just write a for loop. You have your initial condition. Then you do a condition check. You execute your code, and then you increment your conditional counter, and then you check against the condition check again. Then you again execute your code. Then you increment or decrement your conditional variable, do a condition check, and you execute your code. So it's pretty straightforward. There is nothing in it, but let's try to take a small example and see what it is. Okay, so how do you do sum of three numbers using for loop? You have sum equal to 0, and you have i equal to 0, I less than 3, I plus plus, and we have something here, sum equal to sum plus I, right? Fair enough. But this is these are some pictorial pictures that I've drawn on my whiteboard, and I have pasted it here so that it would be more easy for us when we actually visualize recursion, because one of the challenges of recursion is visualizing recursion is kind of tough. So I thought, let's start visualizing a for loop, then we can go to a recursion and all that stuff. So if I have to visualize this piece of code, right now it's all logical computer statements, right? But if I have to really visualize this logic, so then you have something called a small R1, which is our result 1, and then your result 2, and then your result 3. So there are 3 values. You want to compute the sum, and you add R1, the sum equal to R1 plus R2 plus R3. And at every level, there is a state. Like here, initially, my state is R1. Then to it, I'm going to add R2. Then to it, I'm going to add a state R3. And my total sum would be R1 plus R2 plus R3. So this is a basic for loop. There's nothing much here. It's just a visualizing a loop. Okay. Now let's understand what is recursion and what is the basic skeleton of any recursive function. Now this is basically, recursion is a mathematical idea. Even before it was borrowed into programming development or software development, it was a mathematical idea, and it was there from long back. And a simple explanation of recursion is a function calling itself. So basically you have a function which executes a piece of code, and at the end of the code or in the middle of the code, somewhere that particular piece of function will call itself. That's the definition of a recursion. It's like a function calling itself till it accomplishes something. That is the idea of recursion. So now a natural question should arise when anybody looks at this code is, when a function is calling itself, like I have function 1 that will call function 1 again. Now function 1 will call function 1 again. So, it will go into spiral forever, right? So you need to have a break condition so that this spiraling effect will stop. So that's why any piece of recursive code you take, it always have a break condition, and it will have something like you see here, execute something, and then this particular function will call itself. So the most important thing that we need to remember while you understand any recursive code is, apart from the function calling itself, there's always something called break condition. And if you don't have the break condition, you will see errors like stack overflow errors, where, and like, your function has been calling so many times, and eventually your whole heap size has been filled up, or there is no stack space. So those are the errors that you get when you don't have something called a break condition or something like that. So the most critical part of any recursion code is your break condition, your logic, and then you're calling the recursive function once again. So these are the three, this is like a skeleton of any recursive programming construct. Now let's take a small example, try to do that, okay? So I have taken the same example, the recursion code for sum of 3 numbers. We have already taken the for loop example for sum of 3 numbers. Now I want to do the same thing using recursively. So let's think. So the way you need to write a recursive code is your recursion code will solve a problem locally, and then it will call the recursive code with the assumption that it will compute the results magically such that all the global results are accumulated and given back to it. So there's a lot of information that I'm putting on here. Let's take it step by step. Whenever you write any recursion code, it could be anything. It could be greedy recursion code, or it could be a dynamic kind of a recursion code, you name it. The way you need to approach any recursion problem is you first solve the problem locally, and then the remaining part, you assign it to your recursive function with the assumption that it will get it done. So you need to have that much faith on your recursive function that it will do the job no matter what. And then you need to put a break condition, because if you don't put a break condition, it will spiral on forever and you'll get a Stack Overflow error. So in my case, what I'm doing here, I want sum of 3 numbers, right? So how do I do it locally first? So if I have a number X, the way I'll do it is, if I want sum of 3 numbers, I will do X plus, this is a local computation that I'm doing, plus I'm telling my recursion function, hey, you do the remaining job and give it back to me. That's it. You should have that much confidence on your recursion code that it will do it no matter what. So if you see here, I have written it pretty straightforward. Return X plus get sum X minus 1. Now, when do you want to put a break condition? So if you see here, the question tells me that compute the sum of 3 numbers, 3 plus 2 plus 1. And after 1, do I have any number? No, right? So that means the break condition should happen at 1. So what I've written is, if x double equal to 1, if it is 1, you return 1. You don't do much computation. Else, if it's not 1, then you go to the next logical statement, do the computation locally, and give the rest of the job you give to your recursive function. One of the reasons why many people think dynamic programming is difficult, for that matter, if you see on internet, online, you see when you go for reading about dynamic programming or graph algorithms, people always say that this is one of the most difficult concepts in algorithms. Why do they say it's difficult? Because the fundamental problem here is not in dynamic, it's not in the idea of dynamic programming, or it's in the idea of graphs. The fundamental problem is visualizing or writing a recursive code. That is the problem. And in order to understand the intuition in writing any recursion code is always compute the problem locally and assign the rest of the job to your recursive function with the faith that it is going to do the job. So if you see here, I have clearly written return x plus get sum of x minus 1. And if I have to visualize this piece of code, you see here, I have my R3, my function state when the x is 3, and that is going to call the other function state where x equal to 2, and that is going to call another function state where x equal to 1. So you see how recursive in nature these calls are, or how fractal in nature the calls are, or how the calls are stacked up. So this is the picture that anybody needs to have while they're trying to solve any recursion code. Now, moving forward, if I have to visualize the same thing, this is the top view of my recursive code. Now let's take the front view of my recursive code. So I have my R3 where x value is 3. Now what I'm going to do is this particular function will call R2 where x value is 2. And this particular function we're going to call R1 where x equal to 1. And I have already put a break condition here. If x double equal to 1, return 1. So this is going to return 1. And then And when the x value is 2, it will give me 2 plus 1, 3, and 3 will come to my third function state, and 3 plus 3 is 6. So my sum is 6. So I want to stop here. Do you guys have any question? Ask me right now, because only if you guys understand here, then we can take the discussion will become more and more interesting. Otherwise, I need an acknowledgement here, whether you guys have understood or not. I'm not getting any acknowledgement. So you guys.
So yeah, so this is Suva. Sandeep, I think on behalf of everybody, I think we are good so far. So you
guys are good, right?
Yeah.
Okay. So this is the recursive call stack front view, and this is a recursive call stack top view. And now the question is, Sandeep, it's fantastic. Now you're talking about recursive call stack, but how does this happen actually in the memory? Because your code is being executed in the memory, right? That is the most, ultimately everything has to be executed in a piece of hardware, right? So how does that happen? So the way every function, so the way the recursion takes place is, if you see here, every function is stacked up on top of the other function. So there is a stacking, it's like a pyramid, right? So you have the bottom layer, and the top layer will be on top of the bottom layer, and the next top layer will be top of the other two. So it is kind of a stack mechanism. So everybody needs to remember, whenever they talk about recursion, it is always going to be like a stack. The calls are stacked up. So here, if you see, R3 will call R2, R2 will call R1. And once R1 is computed, it will return that computation to R2, that gets computed here, and R2 plus R1 is returned to R3. So there is always this recursive call stack. Please remember this idea that functions are stacked up in any kind of recursion. Why I'm stressing this point is, most of the recursion, after people write recursion, one question that they ask is, in any leave about interviews. Interviews is just one forum where they talk about recursion. Even from any computer science aspect, when you write any kind of recursive code, one thing that is very important is space complexity. You can talk about time complexity because the recursive code have some mathematical formula. You can just plug it, play it, and you can get the formula. But what is the space complexity? Right? So that is a question, right? When you're having recursion, what is the space complexity of that? So in order to answer that question, you need to have this in your mind, that to compute the result R3, there will be multiple stack function calls. And in order to get R3, there will be R2 here, there'll be R1 here stacked up. So just remember this point at the back of your head. And when it's required, we'll bring up this idea in trying to compute the space complexity, okay? Now, this is a basic recursive call stack. So from here, let's talk about, now we have two programming paradigms, right? Let's talk about the differences, recursion versus iteration. It's simple, like recursion is function calling within the same function. A loop is, you execute a piece of code repeatedly till a condition is met. Recursion code execution is slower, obviously, right? Because because you do a local computation, and the global computation, you assign it your recursive function, and that will call another function. Now when it calls another function, it has to set up its own stack space, data space. So there is a lot of time that is involved in execution. So obviously it is slower than a loop. Then here you have a stack used to store the local variables when the function is called. Obviously, because because every function call is stacked up. So that is the reason we have a stack, but that's why they said stack is used to store the local variables. In a loop, obviously you don't have any stack. And as I already mentioned, if there is no termination condition, it can be an infinite recursion. The same thing with the loop. If the condition is not met, it will be an infinite loop. Recursions are more readable, loops are less readable, and recursion space complexity is higher, and loop space complexity is lower. So one point, like everybody talks about is, it is very difficult to think in recursion, right? But how come recursive code is more readable in nature? So why people think that recursion is not a natural way of thinking? Yes, logically, we are linear creatures. We think in a linear fashion. But take about artists or painters. they think in multi-dimensional, you know. So for example, you have artists drawing optical illusion where you have a face, in the eye there is another face, you know. So you need to have certain, like if anybody is writing recursive code, if you have some amount of imagination, then I think writing recursion code should be very easy, fun to do it, and it is very simple. You don't need to write a lot of code. You can just write recursion, and it is so easy and it's pretty fun. But all you have to do is you have to have a little bit imagination in imagining the, you know, problem. Then it becomes more easy. But from this differences, it looks like loop is a better, if you take space and time, loop is a much more, gives much more edge over recursion, right? So let's see in what occasions really, truly we need recursion. When to use, so the other question is when to use recursion, you know? If you have a, imagine a graph like social networking, okay? And now this I have taken from, this is not even a, so this is a graph from a startup company. And you know what graph is this? This is just the communication channels, like what people are messaging, who is messaging to who in a 1 week time span in a startup company in the Bay Area. Now let's assume the startup company, they didn't say how many people are there, but let's assume there are 100 people. So in a week, they found a graph of the communication channel, and this is what the graph they got. You know, this is the graph they were, the data, when the data was analyzed and visualized. So this is the graph they got it. Now, if I really want to traverse this graph, do you really think, or do anybody think, or is it possible with a programming paradigm using iterators? It's humanly impossible. Why? Because, for example, at every level, so if you're doing a linear thinking, if you're in a linear dimension, or if you're moving from one stage to another stage, and there is only one, like for example, I'm moving from stage 1 to stage 2, stage 2 to stage 3, but at every stage there is only one option that I have to execute, or only one path that I have. Then for loops, while loops, or for each, whatever iterative construct you have, it is good. But in a very complex scenario where you see in a kind of social networking, how can you even traverse this graph? It's humanly impossible, right? Because at every stage you have multiple pathways. So you cannot write a for loop in this kind of data model. That is number one. Next thing is, if you want to backtrack the path and go in a different direction. Now, example, I'm on stage 1, I went to stage 2, I went to stage 3. I realized that stage 3 is not the valid stage I am right now. Instead, I should go back to stage 2. And again, from stage 2, I need to go back to stage 4. I'll repeat what I'm saying. I am in stage 1, I went to stage 2, I went to stage 3. Now, I felt that stage 3 is not the right stage where my logic is. So I need to go back to stage 2 and move to stage 4. How can I do that in for loop? There is no backtracking, right? It's only in one direction. But if you want to do in recursion, you can always do that. And then I also said that, what about the scenario where at every level, there are multiple directions in which someone can travel? What I meant is, for example, you imagine a Facebook-like social networking site, okay? Sandeep has 1,000, I have 1,000 friends. And now, if I want to do a traversal of my friend list, starting from me, I can go to my friend 1, friend 2, friend 3, friend 4, friend 5, right? Which friend should I go for? There is no, because at every stage, there are multiple directions in which someone can travel, right? So there is no linear way of traversal, or there is no linear dimension to my multi-stage traversal. And that is the reason for loop fails. Or not for loop, but the iterative programming paradigm fails. So in all the above scenarios, recursion is the only option that we have. Otherwise, it's humanly, we just cannot model the real world scenarios and put it in a computer and program it. And even if you see here, like you see, the node cluster here is same as node cluster here and same as node cluster here. So what we can do is execute all this node cluster and call a recursive function and ask it to execute this node cluster. When I say execute, it could be anything. It could be traverse any operation on this data nodes. And once you execute it, you call the same recursive function to execute this node cluster. So you see how the idea of recursion is being built up naturally. Like when you have to execute the same set of instructions on multi levels, then this whole idea of recursion will kick in and it becomes more intuitive to use. Okay, so this is why we need recursion. And most of the interviews, like when you go for any scalable company, like when I say scalable company, let's assume Twitter. Okay, if you're trying to attend a Twitter interview, one of the questions, it's a standard that they always ask a recursive question. It is given. Like you check in Leetcode or Glassdoor, one question is always on recursion. Why? Because their whole data, when you have a Twitter, right? You have a Twitter message, you have Twitter followers. Now you want to see how the Twitter feed is creating an impact. Now you want to traverse the audience. And how do you traverse it? If you use a loops, you cannot do it, right? You have to go recursively do it, compute the results and give it back to the parent function caller. So all these things are kind of accomplished using recursion. So this is the fundamental idea. So what everyone needs to take from this slide is, whenever you have a complex graphs data model where at every level you have multi-direction to travel, then you'll go for recursion. When you need to do backtracking, when you go forward, you want to come backward, then you need to go for recursion. And in any graph any graph data, you will, by any graph or tree, you always go for recursion. So this is the idea behind recursion. Now let's take a sample problem. This is a sample. This is a very fun problem to do. Why I have taken a problem is because now that we have a certain idea, let's implement it and see whether how this idea can be distilled down and in solving a problem. Okay, and this is fairly this is a Leetcode problem. The medium level of this problem is a DP version of it. So the dynamic programming version of it is a medium level problem, but I'm not talking about the dynamic programming aspect at this point. Let's talk about recursion, how to write a recursive code, how to write a recursion function here, and then we can move forward. Okay, so the question is like this, it's a very fun question. So you have certain number of steps, but there is a restriction on which you can climb, how you can climb the step. That is, you can only take one step or you can take two steps at any given point of time. Now my question is, now give me the total number of ways in which you can climb to the top. So what are the total number of ways in which you can climb to the top? Either I can take one step, one step, one step. That is one way. I can take two steps plus a one step. That is another way. Or I can take one step and I can take another two steps. That is another way. So basically, there are three ways in which you can climb the steps. Now let's take two steps, okay? I have taken two steps. Now, can I take another two steps? No, right? Because if I take more than two, then I cannot, there are no steps available as well. So basically, there are three ways in which you can climb the stairs where I'm allowed to take one step or two steps. Okay, so this is the problem statement. Are you guys clear on the problem statement? I need some.
Any questions, folks? Yeah.
Okay, if there's no question, then I'll move forward.
Yeah. Just hold on 1 second. I think people might ask. The one thing just to clarify here, right? The step, it's a fixed stair and it has 4 steps. So total steps, number of steps is 4. And because there are 4 steps, there are only 3 ways in which you can climb. Either take 1 step at a time, or take 2 and then take 1, or take 1 and then 2, right? So essentially you are, and because there are 4 stages, there are actually only 3 steps, if you will. So just to clarify. So 4 stages, but 3 steps, essentially,
yeah.
Right? So, yeah.
So this is the question. Now, I already told you, even before we look into the code, one thing I told everybody here is, just a minute. How did I solve this recursion code? I told you guys that always solve the problem locally and give the rest of the effort to your recursive function with the assumption that it will solve it globally and and it will give you the solution. Always remember this magic rule. With recursion, you will only solve the problem locally and give the rest of the job to your recursive function with the faith that it is going to solve the problem for you. And you just relax, that's it. So now, when I say solve the problem locally, let's start with step one, okay? When I'm at step one, how many ways I can take steps? I can take one step, or I can take two steps. That is what is given, right? So now what did I say? I said solve the problem locally first. So that means if I'm at my lower step, then either I can take step one or step two, write that piece of code, and then give the job to your recursive function. So by now, this idea now you guys should be able to visualize the recursive function. What I'm telling you, I'm repeating it again. Solve the problem locally first. What do I mean locally? Either I can take one step or I can take two steps. Write that code logic and then give the task to your recursive function with the faith that it will do it for you no matter what. Okay. So now let's write it in mathematically or from programming aspect, whatever. Let's assume we have n steps and f of n be the total ways to climb n steps. There are two ways in which we can climb the steps. Take one step or take two steps. If you take one step, then how many steps you will have? N minus one. If you take two steps, how many steps you're gonna have? N minus two. So that means your recursive function is f of the total number of ways in which you can climb. If, for example, if you're at, okay, let's understand the terminology here. The lowest step is the nth step. The topmost step is the 0th step. Okay, that is the terminology here. Let's take it in that way. That would be a little bit easier in writing the code. The lowest step is the nth step. The next higher step is n minus one. The highest step is the 0th step. Okay. So what I've written, f of n equal to f of n minus one or f of n minus two. So if I've taken one step, then how many steps do I have? F of n minus one plus, or I can also take two steps, right? So how many ways I can if I take two steps, how many steps I have? N minus two. So now because you believe your recursive function, you are saying that, hey, I have taken one step, so please give me the number of ways in which I can climb n minus step. So that means you have written f of n minus one. But you can also take two steps. If you take two steps, what you're going to do? You need to give me the total number of ways you can climb the steps from n minus two. So that's why I have written f of n minus one plus f of n minus two. I'll give a stop here for a few seconds. If nobody has any questions, I'll move forward, or else I can take up some questions here. Okay.
Yeah, hold on, Sandeep. I think let's give people just a few seconds more. Any questions, guys? So remember, the function is returning the number of ways that you can climb, total number of ways. So at any given step, f of n is equal to the number of ways you can climb, taking just one step at that point. You're solving the problem locally, right?
Yes.
Or you can take two steps and then something else. Any questions, clarification? Okay, so I have a question for you, Sandeep.
Sure.
Okay, so now we are solving this locally. I understand the f of n minus 1 is just referring to the first step. So f of n minus 1 is implies that for now I'm taking one step, but subsequently there might be multiple combinations of 1 and 2 steps that may happen, but I don't worry about that. For now, what is the total number of ways to climb, provided I take only one step first?
Yes,
is that assumption correct? Okay.
Yes, that is n minus 1. That's, you're spot on, Suva. Like what you said is can you repeat that, because you have put it in very simplistic terms? Can you just repeat that, what you said?
Okay, so f of n minus 1 basically means giving all the different number of combinations possible to take as many number of steps in the future, as long as the first step is only one. So that's what it means.
Yes.
F of how many number of ways we can climb, provided we take one step first. So we are just solving it locally for one step. And likewise, f of n minus 2 means how many different number of ways we can climb subsequently, provided we start off with taking two steps in the beginning.
Yes.
Okay, Okay, just wanted to clarify that. Okay,
Yes.
so even f of n minus 2 would eventually have one step or two steps later
But
on.
we don't need to worry about that complication because,
Exactly, and that's what you're saying. That's what you're
yeah,
saying.
because
Yeah.
we have so much faith on my recursive function that it will just do the job no matter what.
Yes. Yeah.
But one thing I already mentioned, function calling itself is like a spiral, right? It's like you calling, it's like you call your function is calling itself, that function will call itself. So there is a spiral that's happening. You need to put a breakpoint, right? You need to break it some point so that the spiraling effect will despiral. So let's look at the problem. Where am I breaking the condition? When I've reached my top step, then obviously then I have to, then if I reached my top step, then that means there is one way in which I've reached, there is a way, right? If I've taken 1, 1, 1 and reached top, there is a way. So that means when my n becomes 0, that means there is a one way. However, when I've taken 2 steps and, when I've taken 2 steps, and if I try to take another 2 steps, I cannot take it. Why? Because I have an intelligence that I cannot take 2 steps because there is only 1 step here. Now, computer doesn't have that intuitive sense, right? You need to program it. How are you going to program it? You tell, hey, if your n becomes 0, then you return a path for me. But if your n becomes less than 0, you return 0. That means there is no path at all because computers don't have the common sense, right? We have as humans, if you're standing at step 1 and if you're trying to take 2 steps, we know obviously you cannot do it. But how do you, because we have that intuitive sense, but how do you translate that intuitive sense to a programming construct in mathematical terms for computer? That you have to do it like, okay, if n is less than 0, that means I cannot even traverse, right? Because if I'm at step 2 and I take 2 steps, that means this is my 0th step and that will become my -1. So that means I cannot reach to the top, right? So you return 0. But if I've reached 0, that means I have successfully reached at the top. So return me a path. That means return me a value of 1. The recursive code for the previous expression is count total ways plus n-1 plus count total ways n-2. This is not a complete recursive code because we need to have a break condition. Now, the user will stop climbing once he has reached the end of the stairs because he cannot go further, or he has reached to a point where if he take more number of steps, obviously he will cross the 0th step. But as humans, we have that intelligence. But if you have to put the same intelligence in terms of computer science, mathematical concept, it is nothing but when the count is less than 0, you return 0. If count equal to 0, you return 1. That is the break condition here. Do you guys have any question here? Then I'll move to the main other little bit more stuff. Okay, let me move forward. So the complete recursive code is return count total. Always remember, whenever you write any recursion code, don't go with the break condition first, because the way you need to do is solve the problem locally, give the global task to your recursive function, and then write your break condition. That way you can logically develop your recursive way of thinking. So that's what I've written. If n double equal to 0, return 1, n less than 0, return 0, because there is no path there. And what is a recursion? This is a break condition, and the recursion code is count total-ways n-1 plus count total-ways n-2. And this is the basic recursion code. Now let's analyze this code. That's the fun part when you analyze this code. Okay. So the pictorial representation of call stack. So I couldn't get any internet images of this problem, so I have to draw my own on a whiteboard, and I've pasted it here. So if you see here, your function 3, if assuming, let's go with 3 steps, okay? If you have 3 steps, either I can take 1 step or 2 step, right? Again, at 1 step, I can take 1 step or 2 steps. If I take 1 step, then it becomes 0. And that time I told the recursive function to return 1. But if I take in 2 steps, it becomes -1 and there is no path to it. So 1 is given here. Similarly, for 2 steps, you give 1 and 0 because I can take one step or 2 steps. And at 1 step, again, you can take 1 step or 2 steps. If it 2 steps, it is less than 0, you return 0. If it is 0, And if you have taken one step and you have reached the top of the step where n value is 0, you return 1. And these are the, you see, it forms, so you see the problem inherently as a tree kind of a structure, or because at every level you have multiple options. But if you have only a for loop, if you try to do the same problem, if you try to do for loop, I'm not saying you cannot do it, but what I'm saying is it's close to impossible to write. I mean, you can challenge me, hey Sandeep, that I tried to write this in for loop and it worked. Yes, you can do it in for loop. I'm not saying it, but the complexity of the code will increase exponentially, and at some point you cannot even understand what I'm writing. So, but if you see this code here, the recursive code, it's so simple: count base n-1, count base n-2, and then you put a break condition. And this is and you see the problem inherently has a tree structure to it. And that's where recursion plays very important role. Now, the pictorial representation of the paths. So you have from F3, F1, F0, there is one path. F3, F2, F1, F0, there is another path. F3, F2, F0, there is another path. So basically there are 3 paths. And where F-1 is 0, that's not a path. Where F-1 is 0, that's not a path. Okay. So I'll just wait for 15 seconds or 30 seconds. If you guys have any question, please ask me. Now we are going to a little bit more complex recursion, complex recursion. So I got a chat message here. Let me see what is that. So I have a check this storage there. Okay. So Anand has pointed out that, hey, like instead of, so Anand is asking that, hey, instead of doing n-1, can you start with 0 as a step? So you're going from top to bottom, right? The question didn't say whether you have to go from top to bottom or bottom to top. It just asked how many ways in which you can climb. So I can start from the top step and also go down. Yes, you can do it. There is no harm in it. But as such, you won't find any advantage, because it's like this. Hey, can I do if I want to find sum of 3 to 1, can I write 3 plus 2 plus 1 or 1 plus 2 plus 3? Either you can go from left to right or right to left. The sum is sum. Either you climb from top to bottom, from top stair to the bottom stair to the top stair, or from top stair to the bottom stair. The number of ways in which you can climb will always be the constant. So there is no much advantage you have. Okay. That's one question that I got from Anand. Moving forward. Now let's talk about this is known as, now I'm talking about problem scenarios. That this is a standard problem scenario which occurs pretty much across all graphs, where you have to do a combination of breadth traversal and a depth traversal. That means at every level you have multiple options. You have to choose one option and you have to go depth wise. Then you have to backtrack. Then you again go in another direction. So this kind of program template is across everywhere in recursion. And that is generally people call it as multi-stage single value, multi-stage multi-value, single stage multi-value. There are certain naming terminologies. These are fancy terminologies, that's it. But at the end of the day, it's just how the code, what all stages we have, okay? Now, let's take a scenario. There are 3 stages to your function, okay? And at every stage, you have 3 values, A1, A2, A3, and I want a product of these 3 numbers, okay? Now, as I already told you, what you need to compute locally, and the global effort you return to your recursive function, and eventually you put a breaking condition. I have put the same thing. Get product is equal to A of I into get product of A comma I plus 1, where I plus 1 means initially it starts with 1, then it goes to 2, then it goes to 3. And once that product is computed, when I equal to double equal to 3, I'm not going to go forward. I will just return it back. Now, a question might arise. Why did you even go with recursion? You might as well do with for loop, right? I can do with for loop, right? Yes, you can do it, because at every stage you have a single value. So even though you hop from one stage to another stage, you don't have multiple options. Like for example, if I go from stage 1 to stage 2, instead of A2, if I have B2 and C2, then it will become very difficult to use recursion. I'm sorry. Then it will become very difficult to use for loop. So you have to use recursion. So, but anyways, I started out with recursion because I feel more comfortable with recursion. So I went ahead with recursion. Okay. This is a no-brainer, multi-stage single value. Now single stage multi-value. So in one stage, this is a particular state, and you have to compute the sum of these three numbers. I can do a for loop using a for loop or recursion. I just used a for loop here. Now the question might arise, why can't I use recursion? Obviously you can use recursion, but you know, it's at the same level, you know, at the same level. I didn't feel like doing, you know, a recursion. I felt like let's do a for loop. Okay. So the iterative code for the following operation is sum of a plus e, this is a Java programming construct where plus equal to a of I, where I'm computing the sum of three numbers. So I'll repeat here. This is not mandatory that I have to use recursion, but I just used it. Okay. And it's not mandatory here that I have to use recursion for loop. I just used it. But you need to remember, in both the, whether you take multi-stage single value or single stage multi-value, it is always linear in fact, it's always linear in fashion. You see, this is always, you're moving linearly. You're not moving where there are multiple paths, you know, where there are multiple options. So it is linear in structure. So you can use recursion or for loop, but I used for loop recursion once, and I have used for loop once. Okay. There is no harm to it. Now I'll give you a data template. Now tell me, now we'll think through how do we gonna compute it. Now, how do you gonna do multi-stage multi-value? Now, how are we gonna solve this problem? This is something interesting, right? Because so far we did multi-stage single value. We did it through recursion, which is good. And single stage multi-value, we went through for loop, okay? But now it's multi-stage multi-value. And these are the scenarios that actually occurs in real life. You would be surprised like how many scenarios that occurs in real life with this multi-stage multi-value. One such scenario is your workplace graph. Now just imagine this way. This stage you have all your managers. Here you have all your full-time employees, and here you have all your contractors. So your manager will talk to all your full-time employees, and every full-time employee will talk to your contracting employee. You see the hierarchy here? And there could be multiple managers. For example, multiple managers might be handling this team. This could be a dev manager, QA manager, or a tech ops manager. And so you see, now in a small workplace environment, you have multi-stage multi-value. Not only workplace environment, social networking. Your web search, web crawlers are like this, you know, when you're trying to index all the web pages in your internet repository, you have this multi-stage multi-value. So how do you compute this kind of solution? And by the way, what computation I'm expecting out of this complex data expression? Let's see here. Okay, by the way, so what I want to do is, I want to get the sum of values at every level, the sum of values at every stage, but every value will be multiplied with the values from the other stage. I'll repeat it. What I want is, I want sum of values from every stage, and every value in this stage will be multiplied with the values from the second stage. And the same holds good for the other stages. So when you are B1, what you're looking for, sum of all the values in this stage, but every B1 is multiplied with the sum of all the values in C1, C2, C3. So basically what I want is A1 into B1 into C1 plus C2 plus C3 plus B2 into C1 plus C2 plus C3, B3 into plus B3 into C1 plus C2 plus C3. So A1 will talk with B1, B1 will talk with C1, C2, C3, A1 will talk with B2, and B2 will talk with C1, C2, C3, A1 will talk with B3, and B3 will talk with C1, C2, C3, and the same thing holds good for A2, A3 as well. So now you see there are so many possible permutation and combinations that you need to do in solving this problem. Obviously, when you're hopping from one stage to another stage, you cannot do for loop it is given, because at every level you have so many, so many values, and you need to backtrack. You see, you have to go to second stage. Second stage will go to third stage. It will compute the sum, will give it back to B1, and then plus B2 will go to C1, C2, C3, plus B3 will go to C1, C2, C3. And once you get those values, you add up all those values and give it to A1. And let's see the mathematical expression here. It is sigma, where from 1 to 3 of A into sigma of B into sigma C. So I will pause here for a minute. If you guys have any question, please ask me so that we can talk about this, this thing. Anybody has any question here, or I can move forward? Okay, I think so. Okay.
So we are all with you, Sandeep. I think,
okay.
Yeah. So this, I guess the challenge would be for people to visualize how that function looks like in the expanded form. We all understand, you're multiplying a bunch of A's with a bunch of B's with a bunch of C's, right? That's what you're trying to show here as a summation and product in the top function there.
Yeah.
So conceptually, we understand. I think all of us are mentally trying to picturize how it is going to look like, right?
Okay, sure.
Yeah.
So now, even before, so if you don't think in recursively, so this problem, so let's not even go recursion. Let's try to do it for loop, just to see for the heck of it, why cannot I solve it in for loop? And let's try to, because I tried to do the same thing in for loop and I got stuck in middle, it became too complicated for me. But let me walk you through, guys, with this for loop journey and see how complicated it is. Then we will really appreciate that how simple the problem becomes and so beautiful when you do recursively. You see? Okay, let's do with for loop. Initially the sum is 0. Now, so we have 3 stages, A1, A2, A3. So what I did is sum equal to stage, stage 3 is A1, so stage 3 of I, and then if stage 3 of I double equal to A1, then stage 3 of AI into stage 2 of I into stage 1 sum of this plus stage 2 of I plus 1 sum of this. You see, you're seeing, right? It becomes like, now you need to tell, because why you need to, now you might ask me a question, why do I need to put A1? Why I need this if condition? You need this if condition because if you are trying to compute B1 sum, you need to know what value you're computing at, whether you're computing A1, whether you're computing A2, or whether you're computing A3, or you're at A1 and you move to second stage and you're trying to compute the B1 value. So you see, it just becomes complicated. It becomes messy. You will get confused. And this is a very simplistic example. I've given A2, A3, A1, A2, A3. Now there are more complex scenarios. And in those scenarios, if you try to plug in a for loop or any kind of iterative programming construct, it just becomes impossible. Basically, it becomes impossible to solve it. Now let's do it in recursively, okay? As I already told you, solve the problem locally, give the effort to your recursive function, which does a global effort with the faith that it will do the job no matter what, okay? So what did I say here? So basically what I want here is sum of these 3 numbers. I want A1 plus A2 plus A3, but for every value, I want to increase its value. I want to multiply with the corresponding stages. That's it. Basically what I'm asking it, at every level you do an addition, but when you're doing an addition, for every value, you multiply with the values from the second stage or the next subsequent stage. That's what I'm asking here. See, if you think the problem in an abstract way, what I'm trying to do is A1, is talking to the values from, it's basically talking to these values, B1, B2, B3. Similarly, A2 is talking to, it's at the end of the day, basically what I'm trying to do is here, A1 into all the values of all the values in the subsequent stage. Then A2 plus A2 into all the values in the subsequent stage. Then A3 into all the values in the subsequent stage. And remember the golden rule, do the problem locally, give the task to your recursive function, which does the global effort with the faith that it will do it for you no matter what. So I did the same thing. For int j equal to 1, j less than or equal to 3, j plus plus, sum equal to stage of I of j, and every value I am multiplying with the next subsequent stage. That's it. I will repeat this again. So basically what I'm doing here is, if you see the expression, I am at every level, at every stage, I'm doing an addition. But for every value, I am multiplying that value with the next subsequent stage sum value. That's it. And I'm repeating it for every level. So if you see here, I have written for int j equal to 1, j less than or equal to 3, j plus plus. This is at stage, let's assume at a particular stage, I'm saying sum plus equal to stage of I, but every value is multiplied with the next subsequent level sum. That's what I'm doing, get sum. And once you have written the recursive code, what is a big condition is when you have reached C1, obviously C1 will try to go to the next stage. But do you have next stage? No, right? You don't have a next stage. So what do you have to return? Now, if you return 0, it is a product, right? Because what you're trying to do is A1 is multiplied with the product of these values, right? A1 is getting multiplied with this product of these values. So obviously you cannot return 0. If you return 0, the product will return become 0. Now, if the product has to stay intact, what you have to do, you have to return 1. That's it. It's just 5 lines of code. If I equal to 0, that means if the stage is a 0th stage, return 1. There's nothing more to go. However, if it's not a 0th stage or some other stage, you compute the sum. But for every value, you get the next stage sum. You multiply it and you do the addition. I will stop here for a minute. You guys have any question, please ask me. Somebody posted in the chat. Suva Sharma.
So yes, I was just trying to sort of simplify this so that people think in terms of A, B, and C, Sandeep. So essentially what you're doing is you're computing C1 plus C2 for C plus C3 for every multiplication, and essentially multiplying that once with B1, once with B2, and once with B3, and then taking the sum of
Actually, Suva,
yeah.
no.
So no. Not that I'm trying to interpret how you're doing it in recursion, but isn't this the problem statement? I'm just trying to simplify the problem.
The problem statement, hold on. I will just, I will stop this share and I'll open a notepad. And
yes. Can we share it there? I think
just a minute.
People need to visualize. Yes. People need to visualize what your function is. Yeah. Please.
Okay. I will do a notepad here. And just a minute. Are you guys able to see my notepad here?
Yes, we can see your notepad.
What I'm asking is, this is what I'm asking. A1 into B1 into, A1 into B1 into C1 plus C2 plus C3. Okay. And this one plus B2
and if you could increase your font size.
Just I'll do it. Just a minute.
Thank you.
B3 into C1 plus C2 plus C2 then plus A2 2 into
yeah, it's the same thing. Yes, exactly.
Yeah. Let me just do it.
Yes, essentially what I'd done was given line 1
Yeah.
and then the ellipsis.
So basically,
Okay.
you're seeing, right?
Yeah, yeah.
So this is A1 stage A1, but every value is increased with the values from the next stage. Okay. But when you're computing the next stage, B1, what is the next stage? If I want to get values from the next stage, you need to sum them up. But for every value, you again need to multiply with the values from the next stage. Now you're at C1. Now C1, after C1, the third stage, do you have any other stage? No, right? So obviously that's why I return 1. And this is the expression that I want to compute. You guys are seeing the recursive structure, what I'm trying to present you guys here. So this is what I'm doing here. So if you see, I want at every given a stage, I want the sum of numbers. Okay. But for every sum of number, I need to multiply the value with the subsequent stage. So that means A1 into the values from the next stage. But what is the value from the next stage? B1 plus B2 plus B3. But B1 plus B2 plus B3. But if I do the same, but even at the next stage, the values are also, if I want to do B1 plus B2 plus B3, I cannot do it, right? Because what is the sum? What is the values? So what is the definition here? If I want to get sum of values in a stage, what you need to do is you need to take the value and multiply it with the values from the next stage. Now what I'm doing A1, I'm multiplying it with the values on the second stage. Now second stage, what are the values? It is B1 into the values from the next stage. That is third stage, C1. Now C1, if it has to go to next stage, there is no next stage. So it cannot go next stage. So that is where you need to put your break condition, where I have said that if you are going to a last stage, if you have already crossed your stage limit, then just return 1. So this is C1 plus C2 plus C3 plus B2 into C1 plus C2 plus C3 plus B3 into C1 plus C2 plus C3. Let me stop this part. Let me go back to my slide here. Where is it? Yeah, so this is what I have written here. You see, I want the sum is at every value here. What I'm asking is give me the sum of values at this stage, but every value, when you're doing the computation, you multiply it with the values from the next stage. That's it. So if A1 has to be multiplied with the values from the next stage, B1, B2, B3. But when I try to compute the sum for B1, B2, B3, B1 again will be multiplied with the values from C1, C2, C3. B2 again will be computed, because the condition here is you just don't do a sum, but for every value you multiply the values from the next stage. That is what I'm doing here. What is it? For int j equal to, I'm doing the sum, but for every value, I'm bumping it with the values from the next stage. That's it. Get some stage of I minus 1. And the break condition is just to avoid a spiraling or stack overflow condition. You need to put a break condition, or you need to break your recursion flow. And how do you do it? When your I equal to 0, that means you don't have any other stage. You just return 1. That's it. Are you guys satisfied here, or you guys have any question? Please ask me, because we have sufficient time here. So please ask me here. Because if this is understood, then pretty much the crux of recursion, you guys have got it. But if you guys have any question, then I can help you out. Okay, I think people are good. So moving forward, this is one standard example of, this is being used in the lattice structure. So this is a 3-dimensional lattice where you are trying to move from one lattice to another lattice. But when you're moving, every lattice structure will have an interaction with the other lattice structure. So you see, like you have discrete states at step K, or you can call it any terminology. You can call it a step K, or lattice structure K, or atom K. You can call it, it's just a naming terminology. It's all wordplay. So you have this is a lattice structure, and every node in this lattice structure has an interaction with the other lattice structure. And how do you get the how do you compute there is an operation that takes place between lattice 1 and lattice 2. It could be a product, the operation could be product, division, or any electromagnetic operation, but you need to map the values. So this is one nice example where you'll use multi-stage, multi-value recursion strategy to compute the operations that takes place between lattice A and lattice B. And this is a standard geometry problem as well. I mean, these kind of questions are not asked in interview, geometry kind of problems, but sometimes, you get these kind of questions as well. And if you see, guys, carefully, this also reminds you of a graph where you see breadth traversal and depth traversal. So when you have to do a combination of depth and breadth traversal, that is also multi-stage, multi-value recursion. So now you see, from the level of atoms to the graphs to social networking, backtracking, all these things kicks in this multi-stage, multi-value. And how we are doing it? We are doing it via combination of an iteration and recursion. Okay. And why did I choose here for loop? Why did I choose for a single stage for loop? Is because it is easy for me to do. I can write this one as recursion. I can write this one as also recursion, but writing two recursions is difficult. See, I'm not saying you cannot write it. You can always write it, but I have chosen to do it in for loop so that this traversal is taken care of. And for every value, I just need to compute it at a subsequent stage, right? So I just call my recursive function. That's it. So this is the iteration and recursion example. Now let's compute the time and space complexity. Okay. So let's take the first, what example we have taken is the sum of n natural numbers, right? So what is the time and space complexity analysis of it? So the recursive functions, the time complexity is slightly calculated differently. For example, here, so I'm assuming that you guys have an idea on how to compute time complexity. Because this is right now, I'm not talking how to compute a time complexity. I'm just giving you how to calculate time complexity for recursive functions. So sum of three numbers, the complexity is O of n. You see, it's just O of n because this loop is being run n times. So it is O of n. Okay. Now for recursion, you have to compute first get the recursive relation. That is, first get the recursive relation. Okay. Here, and what is the recursive relation? T of n is equal to 1 plus T of n minus 1, right? T of n is equal to 1 plus T of n minus 1. Now T of n minus 1 will call n minus 2, right? So that is 1 plus T of n minus 2. Now n minus 2 will call n minus 3, right? So that is n minus 3. Now this will call n minus 4. So on up to n times where you reach T of 1. And that will become as, now how many n's we have? 1. N times you have 1, right? So that is n. So time complexity is O of n. So basically, this is very simplistic example. But let's try to compute the time complexity for the stairs problem as well. Let's see what time complexity we'll get. Okay. So here, if you see how many times you're calling so basically the way you need to compute the recursive function is you write your recursion relation, then you do a mathematical computation and see how many times this particular recursion function is being called till it hits a break condition. And once you have that mathematical structure, you just do addition, subtraction, multiplication, whatever operation you're doing based on your recursion operation, and you just give me the value. Now, what is the space complexity? The space complexity is, let's go back to this question, for loop. Or let's go back here. So in a for loop, right, what is the space complexity? What is the definition of space complexity? How much space that you have taken apart from your input. So here I've just taken your input is your array. So apart from input, have you taken any other space? You have just taken a space for your sum variable. So that is O of 1. But in case of recursion, how do you compute space complexity? So what did I say here? I said, I'm sorry, I'm going back and forth. The space complexity is the maximum number of call stacks that the recursion will have while doing the computation. So how many stack calls are present in the memory at a given point of time? How many of them are there at a given point of time? That is the space complexity. And in case of my sum problem, when I'm doing R1 plus R2 plus R3 here, you see, I have three stack calls, R3 plus R2 plus R1. So that means the maximum call stack that I have while I'm computing the recursion. So you will have maximum only when it is hitting, when your recursive call goes to the break condition. That is the maximum spiral that you can have. So from the initial calling function till the spiral condition function, how many stack calls you have? That is the space complexity. Why do we need to go with the maximum? Because space complexity is all about the maximum space that you take, right? So even here, the maximum call stack that you have. And when can you have maximum call stack? You will have maximum call stack when you hit the, when the function, recursive function is at the break condition. So here R1 is our break condition. So the space complexity here is O of n. Why n? Because what is n? If it is 3, then you have 3 stack calls. But if it is 10, you have 10 stack calls. If n is infinite, you have infinite number of stack calls, right? So O of n is your space complexity, and that is how you will calculate the space complexity. Now let's calculate the time and space complexity for the step problem that we have done. And remember this tree structure. Remember this tree structure that I have written here, okay? Oh, sorry, I have given it for multi-stage, multi-values. I did not put it for step one. Let's take the multi-stage, multi-values, okay? So in the multi-stage, multi-value, what did I do? Here, I'm computing the sum n times, right? At a given level, I'm computing n. If there are n elements in my stage, I'm computing it into n times, okay? And then every number, I'm multiplying it with the next stage, okay? I'm multiplying it with the next stage. So this could be stage 3, this could be stage 2 and stage 1. So at every level, I am doing n. If I'm at stage k, then my complexity is n into every level. Every number is being calling the next stage. So you have n times you're executing the loop, and every time you're calling the next stage. That is tk of k minus 1, right? N into tk of k minus 1. Now again, tk of k minus 1 is n into tk of k minus 2. Now assumingly you have k stages. So when this condition will terminate, when you have reached the stage 1. So n into so on up to k times. And this is your stage 1. Will you go more forward than stage 1? No, right? Because you'll hit, that is your break condition. You cannot go forward than that. So what is the time complexity of this one is n into so on up to k times. So that is n power of k. And this is a this is a polynomial in nature. The time complexity is polynomial in nature. And that is why now you see why did they say execution is very slow in case of recursion. You see how much time complexity you are having a polynomial. And if you remember from your time and space complexity discussion, polynomials, exponential and factorials are considered to be slower in nature as your input size increases. Okay. So this is how you compute the time complexity. And the space complexity is what is the maximum call stack that you have while executing this problem. Then let's compute the space complexity for the step problem. The stage problem is simple. Let's compute the space complexity for the step problem. So here, what is the maximum call stack that I can have here at a given point of time? I am just going to the step problem again to compute the space complexity here. This is a discussion I'm having here. So here I am at step 3, okay? Now, what is the maximum call stack? The maximum call stack is the path from my root node to the leaf node, right? To the root calling function, to the breaking calling, to the function which execute the break condition. So that is the maximum path. And if you see here from the properties of trees, this will be log of n. If you have n nodes, the height of the tree is log of n. So here, the height of, assumingly you have n nodes in this step problem, and the maximum call stack is the path from the root node to the leaf node. And if there are n nodes, the height of the tree is log of n. So here the space complexity is log of n, where n is the number of nodes that you have in this problem. That is how you need to compute the space complexity. And trust me, most of the interviewers, they will check for your space complexity. If you're attending a company like, let's imagine you're attending a company for Google, okay? Let's aim for the top company. If you're trying to get into Google, everybody knows, so it is easy to compute the time complexity because it's just a recurrence relationship, you do mathematical computation. But they will ask you, they will pinpoint on the space complexity. And how do you do, and how are we going to do the space complexities? By visualizing the entire recursion tree. That is how you're going to know where you're having the maximum call stack, and you will tell that the space complex, this is the maximum space complexity that you have, how many functions you have in the path from the root node to the leaf node, and that is many. Those are that many number of call stacks are there, maximum call stacks are there at any given point, and that is the height of this recursive tree. Now let's go to the multi-stage, multi-value problem and see how many call stacks we'll have. So even here, the maximum call stack will be A1 will call B3, and B3 will again, A1 will call stage 2, stage 2 will again call stage 3. So at any given point of time, there are 3 call stacks. If you see A1 into B1 plus B2 plus 3, A1 into B1 into C1 plus C2 plus C3. So at any given stage, there are 3 recursive call stacks. So the space complexity would be O of, it will be proportional to the number of stages. It will be proportional to the number of stages. So the most important thing that anybody, if you have to take 3 things from this entire discussion is space complexity is the maximum call stack that you have. When do you have maximum call stack? When your function call stack is hitting the break condition, that is where you'll have the maximum call stack. Second thing is time complexity. You will always compute it through the recurrence relationship. And the third most important thing is how to solve recursion. Always solve locally first, then the global effort, you just throw that effort to that recursive function with the faith that it will do it for you no matter what. And once you have written the recursion relationship, you put a break condition so that you need to tell you need to stop the spiraling effect, right? So you write your break condition. So this is about the time and space complexity. Now everything is good. Let's talk about the step problem again. I want to talk about step problem. If you guys see here, there is one interesting thing. Now I'm talking about dynamic. This discussion will be a segue to dynamic programming. It's 5:26 right now. I will not take more than 5 to 6 minutes on giving an introduction to DP, and then I'll open it for questions, and you guys can ask me any questions. Okay. So if you see this recursive step problem, I am already computing f of 1 here. You guys are seeing f of 1 here, right? But I'm again computing f of 1 here. So there are 2 computations. I'm doing it again and again. I am doing f of 0 here, but I'm again doing f of 0 here. 2 computations of f of 0. Actually 3 computations, f of 0, f of 0, f of 0. Now I have f of minus 1. How many times I'm computing f of minus 1? I'm computing 2 times. Already we know recursion is slower. On top of that, if you pre-compute the same function value again and again and again, then we are not using it properly, right? We are not leveraging the computers properly. Why did I use the word leveraging the computers properly? One of the most important things of computers is they have memory, right? So I think it should ring a bell right now. You're pre-computing something, computers have more memory. You're pre-computing something and computers have more memory. So what it should work. So what I'm saying is, when you're pre-computing the same thing again and again, you might as well store it in your memory and just get it from there, than calling the recursion function and then, you know, pre-computing it again and again. It is painful. It's not painful, but it will take more time. And when you take more time, you're basically, your computer is, you know, you don't need to do extra work, right? When you can store it in the memory. So let's take this recursion. I'm just taking a basic recursion tree structure here. If you see, this is some recursion tree structure. Okay, I just got this thing from internet. There's some recursion tree structure, and by default, it's recursion, right? So obviously it will have its tree structure. And if you see, right, how many times I'm computing f of 4 by 5? I'm computing here, I'm computing here, I'm computing here. Okay, 3 times I'm computing. How many times? And there is another time I'm computing f of 4 by 5. How many times I'm computing f of 3 by 3? 3 by 3, 3 by 3, you know, 3 by 3, 2 by 2. Look at this, so many times, and 1 by 1, 0 by 1. So I am just computing values again and again and again and again, where there's no need for me to do it. When I have memory sitting there, you can just put the value in the memory once you have computed, and you can just check in your memory whether the values are there or not. If it is there, you just retrieve from the memory. If it's not there, then you just compute it and save it in the memory. And that is what the whole idea of dynamic programming is. So dynamic programming is not something, it's not something different. It is recursion. It is all recursion. But you identify where you're gonna, so the only challenging task of dynamic programming is you need to know what all computations you are repeating. And in order to know which all computations you are repeating, you basically need to have a complete picture of your recursion tree. And once you have a complete picture of your recursion tree, then you can say, oh, I am computing these values again and again, so I might as well store it in my memory, which I already have in a computer, right? So I will store it and I will retrieve it whenever I want, instead of pre-computing, instead of computing it again and again. And so I have written the same thing. In the previous picture, we were repeatedly calculating the values f of 3, f of 2, f of 1, 1, but we don't need to do it. We can save it in memory and reuse it. Now, there are 2 ways in which you can save it in memory. One is in the form of a map, and one is in the form of a matrix. You know, the memory model can be different. The way you can, in which you put the values in the memory, the model can be different. One is through a map. You can put the values in a map and retrieve it. How I can put a map? You can say that the key for the map will be this value 3 by 3, and the value of the map will be the function value that this function returns. So my map structure can be 3 by 3 is my key, and the value that it returns. Let's assume 3 by 3 is returning a value 10. So my map structure can be, the key will be 3 by 3 and the value will be 10. So I can store it in the form of a map, or I can store it in the form of a matrix. Now you might be assuming, how can I store it in the form? Matrix is X and Y, right? So when I say matrix, it's row and column, right? So I can store this value in a 3rd row and 3rd column. So I can store this value in 2nd row in a 2nd column, right? I can store this value in a 4th row in a 5th column, right? So when you have a memory, what is memory? Memory is nothing but an array of cells. So you can view them as a map, as a key value, or you can view them as a matrix. So you can use your memory model in the form of a map, or you can use the memory model in the form of a matrix. Okay. Now, if you're using a map, then you call it as a top-down recursion. And when you use matrix, then you'll do something known as bottom-up recursion, kind of a strategy, and you will compute your values and you'll get your answer. So this is all about dynamic programming. So dynamic programming is not something, so basically it's like, I would say the advanced form of recursion is dynamic programming. I don't think people generally take, if you read internet, right? If you go to internet, people say dynamic programming is the most toughest concept. But to be really honest, it's not the toughest concept. You need to understand recursion. If you can understand recursion properly, right? If you can get a hang of it, if you can get the complete, the recursive tree, then you can know like what all computations are being repeated, and you can just put them in a memory model, and accordingly you can just fetch the value whenever you want to compute it. So this is all about recursion. If you guys have any question, please let me know.
So this was a great session, Sandeep. Let's just hold on the floor for a few questions. Guys, please don't hesitate to ask any question that you have, either on the initial iteration concept or subsequent recursion and the intro to dynamic programming, whatever questions you have.
Well, here's I have a question.
Yeah.
So sometimes with dynamic programming, it's hard to determine how I should organize the map or the matrix. So
Okay.
you have any suggestions about that?
Yeah. So when you don't know how to organize your map, right? So what I do, the way I go about in solving the problem is, if I don't know where to put my memory, right? So what I'll do is, I will just go ahead without using any map. So let's take this in an interview context. Okay. So you have a problem, you know, it's a recursive solution, and you also have a idea that I need to do some DP, but I really don't know where to do the DP, right? So what you do is, you first write your recursion code without any memory model. You don't even put any map. You don't put any, you don't put any memory model. You just do a basic recursion. Okay. And let me just, I'll just stop my, I'll share something else here. I'll share my I'll share my notepad and hold on. So you guys are seeing this, right? So let's assume I have a recursion code, something like this, okay? F of, this is my recursion code, f of n-1, f of n-2. This is my recursion code. Now, I have an idea that I can use a dynamic programming tool, but I don't know where I need to do it, right? So you don't worry, you don't need to do memory model. First, write a basic recursion code, okay? Once you write your basic recursion code, what you do is, all you have to do is, you can write something like this, you know? So this is your basic recursion code. Then in the interview, once you write your basic recursion code, what you can do is you can write something like this. Then later on, you create a map for yourself, something like this. And then you write, you just modify your code. Like if you already have a hand that I need to use DP, you just put a comment saying that memory will be used, memory will be added. And then you can write something like this. Int x equal. So you write x, you initialize two variables here like this. So first write down your recursion code, and then later on you add your memory. And how you'll add your memory? You see what all recursion functions you have, n-1 and n-2. So you just say if map contains key n-1. If it contains, then x equal to f of n-1. You see how I'm building up my memory model here. Else x equal to f of n-1 map. So you just add this code, okay? So for every recursive function, because you already know when you have something n-1 and n-2, you're pretty much sure that the calls are going to repeat. Like in the step function, you have seen f1, f0, f2. Now I have taken an example of 4. Now if I take an example of 10,000, then obviously I'll be, so you know n-1, n-2, you will repeat the recursion, right? So how do you gonna, but if you want to add the memory model to it, you just write the recursion. Then later on, you do something like this. Then you create your memory model like this. Similarly for, if map contains, similarly, just repeat the same thing for n-2 and you do it. This is what I have been doing. And so far it's been working well with me, at least in the interviews, wherever I went. If I know that it has to do dynamic programming. There is some amount of dynamic programming involved to it. And I'm pretty sure most of the FAANG companies, they will ask you DP problems. Like Google, Twitter, Facebook, they will ask you DP problem no matter what. And they love asking these kind of questions. So what you do is you start with recursion. You don't go, don't directly jump into dynamic programming, because dynamic is just you're just massaging your recursion. Think in that way. So start with recursion, go with basic recursion, and then you modify your recursion code like this. You add this model. Then if map contains, then then you create your map model, and then you accordingly you put your map. You write this. If it is in the memory, then this one. Else, you just compute the value, put it in put back in the memory, and just compute it. Okay, and do the same thing for f of n-2. Sounds good?
Okay, thanks.
Okay. Any other question?
Yeah, I had a question. Akshat here.
Okay.
So in the last slide, you've mentioned about a top-down and a bottom-up approach.
Yeah.
So what are your thoughts on when one approach is better than the other? Like, where would a bottom-up approach implement better than a top-down approach?
See, okay, let me share my note. Actually, I did not create much slides on dynamic programming, but because questions are on DP, let me share that one. Okay, sure.
Yeah, just to clarify, I mean,
in
terms
sure,
of
sure.
recursion.
I'll do that, not a problem. So basically, the way you need to, I generally, if I am writing the code, right? So always remember, you have only 30 to 40 minutes in an interview, right?
Right.
Because 20 minutes will be mostly conversation. So you at max, you'll write the code for 40 minutes. So try, once you write your recursion, sometimes even writing a recursion code might also become very complex,
Right.
You cannot write it. So what you need to do is, your goal should be writing a piece of code that is very crisp and easy to read. And accordingly, remember, focus on my words, crisp and easy to read. So if you're using a DP with a map model as a memory, and if it's becoming too much of code, then go to memory, then go to matrix. Just tell then how do you go about writing the matrix model of the code, right? Now that might be a question. Hey, Sandeep, now you talked about recursion map model, but how do you write the memory aspect, matrix form of it? So what you need to do is, you tell the interviewer, hey, look, see, the recursion code is good, and I can use the hash map model, but the code is becoming complicated. So if it becomes complicated, there is a condition that if the code is becoming really complicated, then you tell the interviewer that I will go with a matrix model, and I will solve the problem. Then you tell them that this is a recursion function. And then what is a matrix model for this? It will be a single row, right? Because there is one variable n. So you will start, and you will go with and if I have break conditions like n equal to 0, if n double equal to 0, return 0. If n double equal to 1, return 1. Something like this. Then what you do is, you just go ahead and fill up the values using a for loop. Okay, your matrix model. Now you know what is f of 2. It is 0 plus 1. Now f of 3, it is 1 1. F of 4, 2 plus 1. You just fill the matrix and you give. And now if we ask the value of f of 1, it will be the value in the matrix. That is how you do it. But I never went through, whenever I do DP problems, even when I'm practicing it or when I give for interviews, and for that matter, most interviewers, even in interviews, they expect you to write the hash map model first, because that will tell you your thought process, how you're doing it. And one thing I told you that this is bottom-up approach, because you see, I am filling up the matrix from the bottom, that is from the break condition, n equal to n equal. So that's why it is called bottom-up. But in top-down approach, I start with my recursion and I fill up my values.
Right.
So this is about it. Any other questions? I have one question in the chat. It was okay. Any other question? If you guys don't have any other question, I think
we'll just wait for maybe just a minute more, Sandeep. I know this was a very informative session, a lot of content.
I would recommend everyone after this session, right? Whenever you solve any recursive problem, always remember, it is a fact that human beings are linear creatures, linear logical creatures. But how then if we are linear and linear creatures, then the recursion also came from human beings, right? So how can I visualize recursion? People say it's practice. Yeah, there is that's not a complete truth. The actual truth is you need to visualize it. You need some amount of imagination to really look into the problem and think from recursion. Then it becomes straightforward. And if you see fractal programming, I am not sure whether you guys heard of the term fractal. If you see fractal programming, or for that matter, if you're trying to go for any interviews from a company like Adobe, who's heavy much into graphics, the whole graphics is all recursion. Why? Because in graphics, you have to, like if you're doing Photoshop, and in Photoshop, you do inversion of an image. What do you mean by inversion of an image? The whole image is in the form of a tree structure. Now you want to take a mirror image of it. How do you do it? You do it via recursion. You cannot do it through for loop. So those kind of things, right? Or the longest path, the lowest common ancestor, all these things, right? Just you have to tweak your right brain with a little bit of imaginative juice, and you can the code will naturally flow. There's nothing. It's nothing complicated. Trust me, it is simple. It can be done, provided you have some you're patient with your code and just push yourself forward. It can be done.
We'll just take a 30-second quick pause, Sandeep.
Sure.
We'll just see if there are any final questions. Going once, going twice. All right, Sandeep, the session today was absolutely awesome. Thank you for volunteering, for sharing your time with us. Time is very precious, very valuable for everybody. I also want to appreciate all the participants, attending today, and Sandeep, definitely on behalf of BayOne and all of us. Thank you for visiting us again for a second time, and we'd love to have you over for a third time and talk about some concepts of dynamic programming and potentially even fractal programming, as you mentioned. So on behalf of all of us, thank you for your time. Thank you, everybody. We'll see you next Tuesday. Until then, stay safe. Take care. Thank you.
Thank you, Suva, for giving me an opportunity to present. This was actually, to be really honest, this was more educative to me as well, because I have to, come up with because this was something like, it's not like a standard concept, right? This is more from thinking perspective. So it was a good educative session for myself while I was preparing this slide. Thanks for giving me an opportunity, and thank you everyone for listening to what I'm presenting. Thank you very much and have a nice day. Bye.
Thank you, Sandeep. Yeah, thank you all.